Here is a plot with 7 orders of magnitude running along the bottom, which means the model on the left is small enough to train on a laptop, and the one on the right cost tens of millions of dollars in electricity to build. Every point you can see is a real model that somebody actually trained and then measured. And the thing I want you to notice is that they fall on a straight line. Not roughly straight, but straight enough that you could lay a ruler along it. Now, a straight line on axes like these is not an ordinary straight line, because both axes are logarithmic, and a straight line on logarithmic axes means the relationship underneath it is a power law. So what would you expect to see here instead? If you had asked me in advance, I would have guessed at something messy, a cloud of points trending downward, with architecture and luck scattering them around. But no theorem in machine learning produces this line. Nothing about gradient descent predicts it, and the people who first drew it were not testing a hypothesis at all. They were training models of different sizes and writing down how well each one did. That regularity has a name, and the name is doing a great deal of work. People call it a scaling law. The word law is a promise, and the promise is that you can measure a handful of small models, fit a line through them, and then read off in advance how well a model 10,000 times larger will do, before you build it and before you spend the money. So for the next 20 minutes, you and I are going to take that promise apart, and we will find out what the vertical axis actually measures, which turns out to be the same quantity we spent an entire video on last time. Why the line is straight and how straight, where it has to stop being straight. And what changed in 2022, when a single paper showed that almost every large model built until then had been trained the wrong way round. And I want to say the honest thing early, because it gets left out. Nobody has derived this law from anything. We are extrapolating a straight line through a fog, and it has bent before. So start with the vertical axis, because everything else you see depends on what that axis measures. You will see it labeled loss, and what you are looking at is cross-entropy, which is the average number of bits the model needs in order to write down the next token, given everything that came before it. If that sounds familiar, it should, because you met this quantity in the last video, the one that made compression and prediction turn out to be the same activity. A model that predicts well assigns high probability to whatever actually comes next. And a model that assigns high probability to what actually comes next can encode the same text in fewer bits. So when this curve goes down, you are not watching a vague sense of a model becoming cleverer, you are watching a file get smaller. Now look at what that does to the axis. A loss of 2 bits per token over a corpus of 1 trillion tokens is 1/4 of a terabyte of description. And if you drop it to 1.9, you have just saved 12.5 gigabytes of text that nobody has to write down. And any quantity measured in bits per symbol has a floor underneath it, which is the second thing we are carrying over from last time. Claude Shannon proved that no code can represent a source in fewer bits per symbol, on average, than the entropy of that source. And language has some entropy, some genuine, irreducible unpredictability about what a person will say next, so no model of any size, trained on any amount of text, can push its loss below it. So can this curve really be a straight line? No, and you can see why from the shape alone. A straight line on log-log axes descends forever, and this one has a floor it is falling toward. Which tells you the honest form of a scaling law before you have measured anything. You are not looking at a single power law, but at a floor plus a term that decays. Loss equals E plus A over n to the alpha, where E is the entropy that no amount of scale removes, and the second term is the part that scale does remove, with alpha setting how fast. So what is alpha? For model size, the measured exponent comes out at about 0.076, and I would like you to sit with that number for a second, because it looks harmless and turns out to be brutal. An exponent of 0.076 means that to halve the reducible part of the loss, you do not double the model. You multiply it by 2 raised to the power of 1 over 0.076, which is a factor of roughly 10,000. Now watch what happens when you apply that twice. 10,000 times the parameters buys you 1 halving, and the halving after that costs 10,000 times again. So the second step is 100 million times the model you started with. And that is why the straight line is simultaneously the most encouraging and the most discouraging fact in the field. Encouraging because scale reliably works and you can predict exactly how well. And discouraging because it prices every further step in a currency that is already measured in hundreds of billions. But is any of this real, or is it just curve fitting? That is a fair objection, and you should press on it, because if you take almost any downward trend and plot it on logarithmic axes, you will get something roughly straight. That is simply what logarithms do to trends. So here is what makes this one different, and there are 2 things. The first is range. These fits hold across 7 orders of magnitude, and the coincidence that survives a factor of 10 million is not usually a coincidence. And the second is that the fit predicts out of sample, which is the part that should move you. The people who published these curves used them to forecast the loss of models that did not exist yet, at scales nobody had ever trained. And when those models were eventually built, the predictions held to within a couple of %. A curve fit that only describes the data you already have is decoration. But a curve fit that tells you what you will measure next year and is right is behaving like a law. But model size is only one of 3 things you can spend on. So what are the other 2? You can make the model bigger, which is more parameters, N. You can train it on more text, which is more tokens, D. Or you can simply run more arithmetic, which is more compute, C. And the constraint tying them together is close to an identity rather than a discovery. The compute you spend is roughly the size of the model multiplied by the amount of text you push through it. So compute is a budget, and N and D are 2 competing ways of spending it. Every extra parameter costs you tokens you could have trained on instead. And every extra token costs you parameters you could have had. Now, that framing quietly turns a question about size into a question about allocation. And the allocation question is where almost everybody turned out to be wrong. Each of the 3 has its own power law with its own exponent, so look at all 3 together. Loss against parameters with data held plentiful, loss against data with the model held large, and loss against compute when you spend the budget sensibly. All 3 come out straight, and the third one is genuinely strange when you think about what it is. Because compute is not a property of the model at all. It is a property of your electricity bill. And yet the cleanest and most reliable of these curves is the one plotting how well a model does against how much arithmetic somebody was willing to pay for. So what does that imply for everything else you might tune? It implies that 2 research groups with different architectures, different tokenizers, different hyperparameters, and different data spending the same compute, will land at approximately the same loss. The details they argued about for years wash out, and the budget does not. It is worth pausing on why a floor exists at all, because there are two of them and they are not the same thing. One is Shannon's, which is the entropy of language itself, the genuine unpredictability of what a person will say next, which no model beats because there is nothing there to model. And the other is Kolmogorov's, which is subtler. The shortest program that generates a particular text is some fixed number of bits, but no compressor finds it in general, because the shortest description is not computable. So a model driving its loss downward is squeezed between two limits: the randomness that cannot be predicted and the structure that cannot be found. And that reducible term, the A over n to the alpha, is everything in between. It is the part of language that is neither noise nor unreachable, but merely difficult. That, and not raw size, is what a scaling law is actually pricing. So where does the fitted floor land? When you fit the three-term form to real data, a floor plus a parameter term plus a data term, the floor comes out somewhere near 1.5 to 1.7 bits per token, depending on which corpus you use. But that number is not the entropy of English, and the difference matters. What we have measured is the entropy of that corpus, tokenized that way, and the corpus includes boilerplate, duplicated pages, and machine-generated text that is far more predictable than a person is. So change the tokenizer and the floor moves. Deduplicate the corpus and it moves again. And I want to be careful here, because this is exactly where confident-sounding claims get made and should not be. The floor in that equation is a fitted constant. What we have is the number the curve extrapolates to, not a measured property of human language. And treating those two as the same thing is the most common overreach in this whole area. Now let us make the compute axis concrete, because floating point operations are an abstraction and electricity is not. Training a frontier model means a building full of accelerators, drawing tens of megawatts, running for weeks. And the compute number on the horizontal axis of these plots is that building multiplied by that time. So we are not really making a modeling choice here. We are writing a purchase order. And when you plot loss against it and get a straight line, what you are saying is that intelligence, measured as compression, has a price, and that the price schedule is stable enough to plan a company around. Now look at the slope again with that reading in mind. Every equal step to the right is a tenfold increase in money and power, and every equal step down is a fixed fraction of the remaining reducible loss. That is the trade the entire industry is currently making, and you can watch the consequence in the buildings, which keep getting larger. Which brings us to the allocation problem properly. So here is the question in its sharpest form. You have a fixed compute budget, and you can spend it on a large model trained on modest data, or on a smaller model trained on far more data. And the two options cost you exactly the same. So which one lands lower on the loss axis? Until 2022, the field's answer was, broadly, to make the model as large as you can afford. That answer came out of the original scaling law work, and it was read as saying that parameters matter a great deal more than tokens. So models grew, 100 billion parameters, then 175, then larger still, while the amount of text they were trained on grew far more slowly. Now watch what happens when you stop treating N and D as two separate knobs and start treating them as one surface. Here is the loss drawn as a surface over both axes at once, with parameters running one way, training tokens running the other, and height standing for loss, so that low is good and the whole surface slopes downward as you move away from the origin. Now look at the curves drawn across it. Each one joins the points that cost the same compute, a single fixed budget spent in every possible ratio between model size and training data. And each of those curves has a minimum. That is the whole result, and you can see it as a shape rather than read it as a formula. A fixed budget spent badly puts you up on the shoulder of the curve, and the same budget spent well puts you at the bottom of it. Same money, different loss. So follow those minima across every budget, and they trace a path up the surface, a ridge. And that ridge is what compute optimal means, which is less a formula than a route you are supposed to walk along. In 2022, a group at DeepMind trained over 400 models to map that ridge, and found that the entire field had been standing well off it. The rule they came back with is easy to state. For compute optimal training, parameters and tokens should scale together in roughly equal proportion. So if you double your budget, you should make the model about 1.4 times bigger and train it on about 1.4 times more text, rather than making it twice as big on the same data. In round numbers, that works out at about 20 tokens of training text for every parameter in the model. Now compare that with what we had actually been building. 175 billion parameters trained on 300 billion tokens is under 2 tokens per parameter, which puts the largest models of that era an entire order of magnitude away from the ridge. And they demonstrated it in the most direct way available, which is to build the smaller model and win. 70 billion parameters trained on 1.4 trillion tokens, 4 times smaller than the largest model of the era, trained on nearly 5 times as much text for the same compute. And it outperformed it. So what does that actually cost the field? I want to dwell on this because it is not a small correction. It says that a large fraction of the compute spent on the biggest models of that period was, in a precise and measurable sense, wasted. Not wasted because those models were bad, but wasted because the identical budget, allocated differently, would have produced a better one. And that is what we mean when we say a curve has a minimum you are not standing at. So look at the same surface once more, but this time cut it with a plane. The plane is a single fixed compute budget, and where it meets the surface, you get one curve. And if you rotate it, you can see that the curve is not flat at all, but has a genuine minimum, with a steep wall on one side and a long shallow slope on the other. Now, why should that asymmetry matter to anybody? Because being too small for your budget is punished sharply, while being too large is punished gently but persistently. And for years, everybody was sitting on the gentle side, which is precisely why it took 400 training runs to notice. And a mistake that costs you a little every time and never announces itself is far harder to find than one that breaks something outright. So why did the first analysis get the ratio wrong? Not through carelessness, because the arithmetic was fine. The difference was in how the learning rate was scheduled over the course of training. In the original work, the schedule was tuned for one training length and then reused across models of very different sizes, which quietly handicapped exactly the runs that used the most data, so the data axis looked less valuable than it really was, and the fit duly recommended spending on parameters instead. And I find this the most instructive part of the whole episode. The law itself was not wrong. The measurement feeding it was mildly biased in a way that nobody thought was important. And that bias propagated straight through into a recommendation which went on to shape billions of dollars of hardware purchasing. An empirical law inherits every assumption of the experiment that produced it, and you rarely get to see the assumptions. But if the right ratio is 20 tokens per parameter, do you see the problem waiting at the end of it? A model with 1 trillion parameters wants 20 trillion tokens of training text, and 10 trillion parameters wants 200 trillion. And the high-quality written output of humanity is simply not that large. Estimates of the usable public text on the internet land in the low tens of trillions of tokens, which is the same order as what the largest current models already consume. So the data axis, the very one the chinchilla result told everybody to lean on, is the axis that runs out first. And that is why the field is now doing all the things it is doing. Training for multiple passes over the same text, generating synthetic data with models in order to feed other models, and reaching for video and audio and code. The ridge is still there. We are just running out of room to keep walking along it. There is one more thing this law gets asked to explain, and I think it explains rather less of it than people say. The claim is emergence, that particular abilities appear suddenly at some scale, absent in the smaller model, and present in the larger one, with nothing in between. And you can see why that would be unsettling. Because a smooth, predictable loss curve with sudden discontinuities sitting on top of it means the thing you can predict is not the thing you actually care about. But now look at how those abilities are usually measured. Very often the metric is exact match accuracy, where the model gets full credit for a completely correct answer and nothing at all otherwise. And a metric like that is a cliff by construction. The underlying probability of the right answer can rise perfectly smoothly, while the score sits flat at 0 and then jumps because you built a threshold into the ruler. So what happens when you score the same runs with a continuous metric instead? Measure the probability the model assigns to the correct answer, rather than whether it gets it exactly right. And a great many of those cliffs turn back into slopes. So a good part of emergence is a property of the measurement rather than of the model. But I want to be careful not to overclaim in the other direction, because that would be the same error with the sign flipped. Not every discontinuity dissolves under a kinder metric, and there are real threshold effects. A chain of reasoning either holds together or it does not, and half a valid argument is not half as useful as a whole one. So the honest summary is narrower than either camp's version. Smooth loss does not guarantee smooth capability, and a graph that looks like a sudden awakening usually deserves a look at its vertical axis first. So let us collect what this law does and does not say, because the two get mixed together constantly. We can say that loss falls predictably with scale, that the fall is a power law, that it has a floor underneath it, and that for any given budget there is a best split between model size and training data, all of which is measured, reproduced across labs, and has predicted out of sample. But it does not say that loss is the thing you want. Loss is bits per token on a corpus. You should treat it as a superb proxy and never as the target. And every gap between the two, factual reliability, calibration, whether a long argument holds together, lives inside that difference. And it does not say the line continues either. What we know is that the line has continued so far, across the range that anybody has been able to afford to test. But there is a version of this argument that goes one step further, and it is why all of this connects back to where we started. If loss is bits per token, and bits per token is compression, then a scaling law is a statement about how the cost of compressing human text falls with the resources you throw at it. And the argument in the last video was that compression, done well enough, becomes indistinguishable from understanding. That to predict the next word of a physics paragraph, you have to have absorbed some physics. So put those together and the scaling law becomes a price list for understanding, denominated in floating point operations. But do you believe that? I do not quite, and I want to say why, because the claim smuggles in an assumption that the last bits are the same kind of thing as the first ones. And they are not. The early bits are spelling and grammar. The final bits are the hardest inference in the corpus, and nothing in the mathematics says the exponent stays the same as you move between them, which leaves the actual state of the question, and it is less tidy than either the optimists or the skeptics tend to present it. We have a relationship that has held over 7 orders of magnitude, that predicts out of sample, that has already been corrected once in a way that cost the field billions of dollars, and that nobody can derive from anything more fundamental. So compare it with the law it keeps getting named after. Shannon's bound is proved. It follows from the definition of entropy, and it will still be true in a century. But a scaling law is not that. What we have is a regression through the region we could afford to explore. And that does not make it worthless, because nearly all of engineering runs on empirical relationships with no derivation, and the bridges stay up. But it does mean the right posture is the engineers rather than the physicists, trusted inside the range you have measured. And treat every extrapolation past that as a bet whose odds nobody has told you. I keep coming back to how all of this must have looked from the inside. Somebody trained a handful of models of different sizes, plotted the results, and noticed that the points were collinear. And you should notice that this is the whole discovery, with no new mathematics and no theorem. Just a straight line where there was no particular reason to expect one. And out of that line came a decade of planning, budgets, chip orders, buildings, an entire industry organizing itself around the slope of a graph that nobody can explain. I find that genuinely remarkable and slightly precarious. Because the honest reading of the last few years is not that we found the law governing intelligence. It is that we found a regularity, mistook its constants for its structure once already, corrected it, and are now extrapolating the corrected version a long way past anything we have actually measured. The line has bent before. It would be strange if this were the last time.